Swayam Prabha. Digital India. Educated India.
Jnanam paramam dhyayam. Knowledge is supreme.
We will do today discrete valuation ring. Some of this might be repetition for you, but still I want to do it for the sake of completeness. So, let K be a field. So, I will give a connection between the discrete valuation rings and normal domains, and then we will do next lecture probably we will start Dedekind domains. K be a field. And for discrete valuation, V of K is a map V from K to Z union infinity, which satisfies the following three properties. One, V of x equal to infinity if and only if x is 0. 2, if I restrict V to k cross, so it is a map from k cross to Z. This is a non-trivial group homomorphism. Where k cross is a group under multiplication and Z is a group under addition. So, this means there is at least non-trivial, so everybody can't be 0. So, at least one element of k cross should go to other than 0. That means this image of V of k cross is non-zero, and also to spell out V of xy equal to Vx plus Vy. That is the meaning of group homomorphism. Automatically it will go 1 will go to 0. And the third one, V of x plus y is bigger equal to the minimum of Vx Vy. Such a thing is called a discrete valuation. I just couple of words about discrete. Normally one studies general valuations, but then this side Z union infinity will be different group, for example real numbers or even bigger group. So, those are not discrete groups. This, because of that, this is called a discrete valuation. Okay, so examples, few examples. This abstract definition came from these classical examples. So, suppose I have a prime number P. P is a prime number. Then, and our field is Q now. Q is our field. You see, it came from the following. If you know, by a fundamental theorem of arithmetic, every integer n we can write it as sign, that is plus minus 1, and a product of prime numbers. So, P1 N1 PR NR, and for the uniqueness, so this epsilon is plus minus 1, and P1 to PR you arrange in this way: P1 less than P2 less than PR, and these N1 to NR are the positive integers. Then one you might have seen in the school that the standard notation for this power N1, which is the highest power of P1 occurs in N, is the standard notation was Vp of Vp N1, Vp1 of N, this is N1, and so on. Vpr of N is NR. So, in general we can write in a compact way any integer n, we can write it as sine of n times product is running over p in prime numbers, p power Vp n, where Vp n is 0 for almost all P in P. Only finitely many Vp of n are non-zero. This gives you also nice identification Z with plus minus 1 group, product cross product is running over P, n power round bracket P. This is an isomorphism. So, these VPNs are the standard discrete valuations. This VP map, think of VP is a map from Z, or and also you can define it for Q. So, you can think it is generally it is a map from Q to actually N union infinity. Oh, no, for Q therefore, we have to take Z here. So, these are the discrete valuations. Each P will give you a discrete valuation on Q, and there is one extra that we will see. And these we can imitate, nothing special about Z, you can imitate for the polynomial ring in one variable over a field which is a PID. Okay, so little bit of notation. So, for each valuation, discrete valuation on K, we define RV. This is by definition all those elements in K such that the, so V of x is called a value of V at x. This is non-negative, and in this MV is all those x in K such that Vx is strictly bigger than 0. Then I want to note that this RV is called a valuation ring of V, and it is now very easy to check that first of all we know V of 1 is 0 because it is a group homomorphism, and if x is in RV but not in MV, then V of x must be 0, and once this is 0, V of x inverse is also 0. So, x inverse will belong to RV. So, that means all those x for which v of x is 0, they are units in RV. So, therefore, actually non-units form an ideal. Therefore, this shows that RV is a local ring with the maximal ideal MV. We are going to study these rings more precisely. So, one final definition here. When I say a normal domain, no, not normal, the DVR, discrete valuation ring, an integral domain A is called a DVR, discrete valuation ring, if A equal to RV for some discrete valuation V of the quotient field of A. This is the standard notation we are using for the quotient field. Such things are called. And as usual, normal, when we say normal domain, that includes the definition, includes it is Noetherian. So, I will just record again. Normal domain means this is Noetherian, integrally closed, integrally closed means in its quotient field. Domain, it is called normal domain. So, now we want to see what is the relation between DVR, normal domains and dimension and so on. So, that is the theorem. So, this theorem we will prove. This gives a characterization of discrete valuation rings. So, A is integral domain, and QA is the quotient field. Then the following are equivalent. One, A is a DVR. That means A is the valuation ring of some discrete valuation ring. 2, A is a local PID. PID means every ideal is principal, and local means there is only one maximal ideal, and of course one has to add A is not a field. Okay, 3, A is local, normal, and dimension 1, cool dimension 1. That means every non-zero prime ideal is maximal. Okay, fourth one, A is local, normal, and the maximal ideal M, and the maximal ideal M is associated to some non-zero element. This belongs to associated primes of A mod A for some non-zero A in M. 5, A is Noetherian local, and the maximal and its maximal ideal M is non-zero and principal. So, proof: one implies two. So, many of these proofs are simple. So, we want to prove now A is a PID and it is not a field. So, and we have given it is a discrete valuation. So, write A equal to RV. We have seen above that A is local, RV is local, we have seen above. Also, we have seen that the quotient field of RV is same as quotient field of A, which is the field K, this discrete valuation on the quotient field of A. So, by condition 2 of the valuation, which says that it is a group homomorphism, that shows that there exists at least one non-zero element, one element x in K cross, such that Vx is positive. If x is not, then x inverse will be positive. So, in any case there is one x, so that it is positive. So, therefore, this x will belong to the MV, and therefore, MV is non-zero. MV is non-zero. Therefore, A cannot be a field, because the maximal ideal, we saw that RV has the maximal ideal MV. So, therefore, A, which is RV, is not a field. So, what did we say? It is a local, not a field. Now, I want to show it is a PID. Okay. So, take any non-zero ideal A is an ideal in A, non-zero. I want to show it is principal. Now, let us take n equal to the min of all the values of A, where A varies in A. So, because we already showed that A is local and this is an ideal, and we can also assume it is proper ideal, because otherwise nothing to prove. So, A will be contained in the maximal ideal. Therefore, all actually these guys is a subset of n. So, this value is a subset of n. So, it will have a minimum. So, minimum exists. So, that means there is an A. So, there exists an A in A with V of A equal to n. But then A cannot be 0, and now you choose B, a arbitrary B. I want to show that this A is the generator of A, the ideal A. So, take any B in A, any B, and then look at VB. VB is bigger or equal to n is V of A. So, therefore, by the property, that group homomorphism property, that V of BA inverse, which is VB minus VA, which is bigger or equal to 0. Therefore, this side, so this means BA inverse, this belongs to the ring, discrete valuation ring. given by V. So, B A inverse is in A, but that will mean that you multiply by A inverse, either I write this way or that is same as A inverse B. Now, multiply by A, so you will get B belongs to ideal generated by A. So, that altogether we have shown that A is generated by A. So, A is principal. Okay, now 2 implies 3. 2 implies 3. So, what is in 2? What is extra? So, local PID not a field, local it is there. Now, I want to show PID, therefore, dimension is 1. Now, I only have to show it is normal with this assumption. So, that means I want to show it is actually we will show that it is a UFD. Okay. So, it is since A is a PID that is given in 2, it is Noetherian, and A is UFD, because PIDs are UFDs and UFDs are normal, we have already proved, or already you know UFDs are normal. So, that proves 3. 2 implies 3 is proved. Now, 3 implies 4. 3 implies 4. 3 implies 4. So, 3 is a local normal dimension 1. So, 4 is normal, local, and the maximal ideal is associated to some non-zero element. So, take a maximal ideal, take the maximal ideal M, the unique maximal ideal M, and this is note that this is the only maximal, this is the only non-zero prime, is the only non-zero prime ideal in A. Because dimension is 1 and it is local. If there was prime ideal different from non-zero and different from M, it will be contained in M and the dimension will increase. So, this is only maximal ideal, this is only non-zero prime ideal. That means, when I take any non-zero element, A is an element in M, and if A is non-zero element, and if I look at the associated primes of A by A, the only element here will be M. But there can't be any other prime ideal, because it will contain A and it will be contained in M, therefore, that is the only prime ideal. But this means, precisely this means M is associated to this. So, that proves 4. Now, 4 implies 5. Okay, 5. So, local 4 is given local, normal and maximal ideal is associated to some non-zero element, and 5 is Noetherian, local, and its maximal ideal is non-zero and principal. So, we will prove. So, Noetherian is already there, because we are assuming normal is Noetherian and local is also there. So, now I only have to prove that the maximal ideal is non-zero and it is principal. So, we know that take the maximal ideal, we know this is associated to some non-zero element of A non-zero. So, in particular M is non-zero, because A contains this A which is non-zero, and therefore, there exists this is M is associated means. So, there exists an element X in A, so that this M is a colon ideal, annihilator of X mod A, but that means M equal to ideal generated by A colon ideal generated by X. But this will mean because okay, so this will mean what? This will mean that if I take any element of M and multiply by x A inverse, I will go in A. See, to check this, I have to check that M times x is contained in A, but that is the definition of this column. So, this is because of this M times x is contained in the ideal generated by A, but that means this multiplying A inverse from this side. So, it is this. So, that shows that this one. So, so M x A inverse, this is an ideal in A. And I want to check that now if suppose this was a proper ideal, M x A inverse is not A proper ideal, then what happens? Let us see. Then it has to be contained in the maximal ideal. Then M x A inverse will be contained in M, but then that means that this element x A inverse is integral over A. That is one of the characterization for integral elements. If you have a finitely generated module, so that M times that is contained in this, then it is integral. So, this is the same to prove this you use the same trick as this Cayley-Hamilton trick. Okay. So, but now because A was in 4, we had assumed that it is normal and this is an element in the quotient field, the A is normal, therefore, this will belong to A. Since A is normal, but this will mean 1 belongs to this colon A Ax. This means precisely this, but this is M. So, it is a contradiction. Maximal ideal is a proper ideal, 1 belongs there. So, this cannot be true. So, that means M x A inverse has to be A, but this will mean M is generated by A x inverse A. So, we actually cooked up a generator. So, its principle.